Hello everyone, this is Moshmi. Today I am here with some selected problems on laws of motion. So the first problem, on a frictionless horizontal plane, a bob of mass m equals 0.1 kilogram is attached to a spring with natural length L naught equals 0.1 meter. The spring constant is K1 equals 0.009 Newton per meter when the length of the spring L is greater than L naught and is K2 equals 0.016 Newton per meter when L is less than L naught. Initially, the bob is released from L equals 0.15 meter. Assume that Hooke's law remains valid throughout the motion if the period of the full oscillation is t equals n pi in seconds, then the integer closest to n is. So, we are talking of motion of a spring here. There is a horizontal plane on which there is a bob, and that bob has got a mass of 0.1 kilogram and it is attached to a spring. So, let us visualize this. We have a horizontal plane. On top of that, we have a bob whose mass m is equal to 0.1 kilogram. It is attached to a spring and the spring is attached to a rigid support again here. The natural length of the spring L naught is equal to 0.1 meter. Now, the spring constant of the spring is it is equal to K1 say, which is equal to 0.009 Newton per meter. This is when L is greater than L naught, and we have the spring constant K is equal to K2, which is equal to 0.016 Newton per meter when L is less than L naught. So these are the two conditions for the spring constant. The natural length, as we can see, it is equal to 0.1 meter. Now initially the bob is released from L equals 0.15 meters. So what does this suggest? It suggests that the original length, the natural length when the bob was not stretched, that was equal to 0.1 meter, but then the bob got stretched through some distance when the length of the spring got stretched, and from this position, this length is equal to 0.15 meter, and from this position, the bob gets released, which means that it will follow the to and fro motion here. So this is the motion of the spring. So what we need to understand here is that initially the original length of the spring together with the bob tied to one of its ends was equal to 0.1 meter, but then the bob was pulled through an additional distance such that the total length now became 0.15 meter. So during that stretch period, the bob and the spring had got a spring constant equal to that of K1. And when it was released and it started the to and fro motion, then for the remaining half time, the spring constant changed to K2. So this is the point which we need to note here. That is, the spring constant is K1 for 1/2 of the time period. We are talking of the time period of oscillation of the spring, and the spring constant is K2 for the other half of the time period. We need to find here the time period of the full oscillation, and that should come out as equal to n times pi where in seconds, where n is some integer. And what we need to do is that we need to find the value of that integer. So what we need to do here is find out the total time period. So the time period for a spring, the time period bears the formula 2 pi root over m by k. This is the time period for a spring. Now in this case, since the time period for one half, the spring will bear a spring constant of k1, and for the other half, it will bear a spring constant of k2. So the time period is actually a combination of two different time periods. So let us write that. We have half for the first part, that is we have pi root over m by k1. This is for the first half, and for the second half we have it as pi root over m by k2. So let's work this out. We have pi root over m is equal to 0.1 kilogram and k1 is equal to 0.009. Plus we have pi times, this is again 0.1 by k, which is equal to 0.016. So we can write this as pi, and what's this? This is nothing but, if you remove the decimal and try to look at it, it is 1 by 0.3 whole square. And for the second part, it is actually 1 by 0.4 whole square. So at the end we have t as equal to pi by the square and the 2. The square roots half and the 2 gets cancelled out. We are left with 0.3 in the denominator, and for the second term we have in the denominator 0.4. So this gives us a total, if we take the LCM, it comes out to be 0.12, and on the numerator we have 0.7 times pi. So this is the time period. Now if we put the values, we get time t as equal to, if we calculate this, this is around 5.83 times pi. So if you consider the original relation, the time here we have got it in the SI units, as all other quantities were in the SI units. So the time period, this can be compared with the original relation as n pi, and from here we may write that n is nothing but equal to 5.83, which is almost equal to 6. So this is the answer here. We have n equal to 6, the nearest possible integer. Now let us look at another such sum. Okay, a horizontal force F is applied at the center of mass of a cylindrical object of mass m and radius r, perpendicular to its axis as shown in the figure. The coefficient of friction between the object and the ground is mu. The center of mass of the object has an acceleration a. The acceleration due to gravity is g. Given that the object rolls without slipping, which of the following statements are correct? So let's have a look at the diagram. We have a cylindrical object. The mass of the object is m and its radius is equal to r. A horizontal force F is applied at the center of mass and it is perpendicular to the axis. the coefficient of friction between the object and the ground, the coefficient of friction is equal to mu. So this will give rise to a frictional force in the opposite direction, which is given by little f. The center of mass of the object has an acceleration a. The acceleration due to gravity is g. Now here we need to consider that the object is rolling without slipping, and we are to test which of the following statements are correct. Now let us apply Newton's second law of motion and write down the equation of motion for this particular case. F is the force acting, so we have F and we have the frictional force getting subtracted as it is in the opposite direction. So F minus little f is equal to m times a. So this is using Newton's second law of motion. So as we know, the torque acting on the body may be written as F cross R, or we can write it as Fr in fact. Let us not give the cross symbol. We have Fr and this is equal to I alpha. Now what's I here? I is nothing but the moment of inertia of the cylindrical object about an axis which is perpendicular to it. So from here we may get F is equal to I alpha by R. So let's use this here. We have in terms of F, I alpha by R, which is equal to ma. Now alpha is the angular acceleration, and as we know that linear acceleration a may be written as equal to R alpha, where R is the radius here, the radius of the cylindrical object. So from here alpha may be substituted as a by R. So let's substitute the value of alpha here. We have F equals ma plus I a by R square. So what we are trying to find out, for the first condition that we are going to test, we need to find out an expression for the acceleration. So let's do that. We have A equals, let's do this step, the extra step, let us do this. We have F equals A times m plus I by R square. So we can see from here that A is equal to F by m plus I by R square. So this is the expression for the acceleration. Now let us test the first condition. The first condition tells us that for the same F, the value of A does not depend on whether the cylinder is solid or hollow. So let us analyze the relation that we got. We see from here that the acceleration A for the same F, it will depend on the moment of inertia I. That is one of the parameters that is affecting the value of the acceleration. And as we know, moment of inertia for a solid cylinder is different from that for a hollow cylinder. So of course, for the same F, A is dependent on the moment of inertia. That is, in fact, we can say that the value of A does depend on whether the cylinder is solid or hollow. So the first statement is not correct. So this is an incorrect statement. Now let us look at the second condition. But before going into that, we shall try to find an expression for A for a solid cylinder. So let's do that. For a solid cylinder, the case of solid cylinder, we have I is equal to half m R square. Now for a hollow cylinder, we have I moment of inertia about an axis passing through the center. I is equal to mr square. Let's substitute this value in this expression. Then we are doing this for a hollow cylinder. We have A is equal to F by, if you see, if we substitute I as mr square, then we get A equals F by 2m. So we can see that for a thin-walled hollow cylinder, A is equal to F by 2m. So this is a correct statement. Now we have one additional condition given in the question, and that is the object rolls without slipping. So we are to use this here. Since the object rolls without slipping, so we may apply the condition here that if an object is rolling without slipping, then the frictional force F, the frictional force actually here will be less than equal to mu mg. So let's use this expression in the relation of F that we have. If you can see, we had little f as equal to I a square by r. Little f was equal to I a square by r. So this f is less than equal to mu mg if the object is rolling without slipping. So from here, using this relation, let us again find out the value of the acceleration for testing the second condition. Now before that, if you can take note, the third condition is also getting proved here. The magnitude of the frictional force on the object due to the ground is always mu mg. So this is again incorrect, as we know that for an object which is rolling without slipping, the necessary condition is that the frictional force may be less than or equal to mu mg. It is not that, it is always equal to mu mg. So this statement is also found to be incorrect. So we are left with only one condition to be proved, and that is for a hollow cylinder, the maximum possible value of A should be mu mg. So let's try to work this out from this particular relation. So if you can see, let's see this relation again. We have some space here. So what we had is F, which is equal to I a square by r. This is less than equal to mu mg. So from here, if we try to find out, we can see that a square is less than equal to, okay, this relation, this was IA by r square. Let's work this out. This is IA by r square. So working this out, we have A less than equal to mu mg r square by I. Now, we were left with the case for a solid cylinder. For a solid cylinder, I is equal to half mr square. So let's substitute this here. We have A less than equal to mu mg r square by half mr square. So if you can see, we get that for a hollow cylinder, A is less than equal to 2 mu g. So this is the condition that we obtain for a solid cylinder. So let's test the option again. So here the option was For a solid cylinder, the maximum possible value of A. So we had got that for a solid cylinder, we just now got that the maximum possible, we got the possible value of A. A should be less than equal to 2 mu G. So from this we can say that the value of A, the maximum possible value of A will be nothing but equal to 2 mu G. So this option in fact is correct. So we had sorted out some important problems for you. Now there are still many more problems. Stay tuned with AppDemi. Thank you.